All right, so in this video, we're going to talk about how to parameterize a surface with a vector valued function and actually use that to find the surface area. So for starters, recall from 21C, there was a section in there when we were talking about the cross product where we came across an interesting application of the cross product, which is that it can be used to find the area of a parallelogram. Here, if you have a parallelogram spanned by two vectors, the area of a parallelogram is just the length of the base times the vertical height. The length of the base is just the magnitude of vector v, and the height, if you solve for it, it's going to involve the opposite on the hypotenuse, ends up being the magnitude of u times the sine of the angle between those two, and you would recognize that that is the magnitude of the cross product of either v crossed u or u crossed v. So that's the magnitude. I'll just put u cross v. And back in 21C, it probably seemed kind of cool, but okay, why are we ever going to want to know the area of a parallelogram? Seems kind of random, but we're going to see in this section how we can use that to our advantage. So to set this up, recall at this point, we know how to parameterize a curve in 3D space, usually with a vector valued function of just one variable. Some examples we've seen, common ones, a circle is a curve, x squared plus y squared equals 1. And we saw that we could parameterize that by letting x be cosine of t, y be sine of t. And so we can think of it as a vector valued function of just cosine t, sine t, having t go from 0 to 2 pi, traces out the curve. If I wanted to find a vector valued function for a part of a parabola here, y equals x squared from -1, 1 to 1, 1, I could just let x be t, if x is t, y is t squared. So there's my vector function, and I would just let t go from -1 to 1, and that would be a vector function that describes that curve. So perhaps, or maybe not perhaps, not surprisingly, we can parameterize a 3D surface, a whole surface, not just a curve, right? Those are just lines or curves in space, a whole surface, using a vector valued function and with two variables. We need an extra variable to do a surface. For a curve, you can usually do it with one variable. So as an example, let's find a parameterization for the surface of the cylinder, x squared plus y squared equals 1. That's a circle in the xy plane, but if we let z vary from 1 to 4, that would sweep out a cylinder. And so how we would do that, I could let, just like we did for the circle, I could let x be cosine of t, y be sine of t, because it's a circle of radius 1. And I could just let z be z. I could just let it be what I want it to be. I could just let it be z. I realize here, let's call this cosine of theta. I could have used t as well, but let's use theta because that represents the angle. So my parameterization could be cosine theta, sine theta. That traces, any point on the surface is always going to fall on that circle of radius 1, at least the x and y. So that should be familiar. But then if we just let z be z, and we let z vary from 1 to 4, and of course theta is going to go from 0 to 2 pi, that can describe every single point on the surface of this cylinder. If you tell me what angle we're at and tell me what z value you're at, we can find any point on this surface. So one thing we can do with that, it's out of view there, is now we can use this to find the surface area of this cylinder. And this is where that thing about 21C, the parallelogram, comes in. If you can imagine the surface of the cylinder as being broken up into a bunch of little tiny, infinitely small parallelogram patches, I like to think of them as, a whole bunch of them around this cylinder. And we can describe a parallelogram. We can form this parallelogram by two vectors. At any point, there would be a vector, the partial derivative of my vector valued function with respect to theta and with respect to z. You could probably picture if I was going to change theta, that would go this way, right? It goes around the circle. That's why r sub theta is pointing that way. And if I was going to change z, that would go upward. So you can imagine a small little patch like this forming a parallelogram. They're not necessarily perpendicular. That's just the way I drew it. Then we know the area of that small little patch from 21C is the magnitude of r sub theta crossed with r sub z. And the idea is we can add up all of the parallelogram patches all around the cylinder. In other words, we can integrate this cross product, magnitude of the cross product, over the surface. Now I changed the general formula. It doesn't have to be theta and z that we use as our two parameters. So generally we would just have u and v, and you just integrate over the surface. So for this example, we have our r sub theta z, cosine theta, sine theta z. And I would need, this is the partial derivative of my vector function with respect to theta. So that's going to be negative sine theta, cosine theta, and 0. So that would be treated constant. And the partial derivative of my vector function with respect to z, theta would be constant. So I'd have 0, 0, and the derivative of that would be 1. Then I would do my cross product, r sub theta crossed with r sub z, negative sine theta, cosine theta, 0, 0, 0, 1. Cross product, block out the row and column, and we do the determinant. So cosine of theta times 1 minus 0 is just cosine theta. Remember, the j component automatically gets a negative. Block out the row and column j's in. Determinant is negative sine of theta minus 0. So it's the negative of negative sine theta, which is positive sine theta. And for my k component, row and column blocked out, determinant is 0 minus 0. So that's just 0. And then the magnitude of the cross product is what we need. So since we just end up with cosine theta, sine theta, the magnitude is the square root of cosine squared theta plus sine squared theta. That's our favorite trig identity. That's just 1. So it turns out in this case, the cross product's just 1. So my surface area of this, I would set up the integral. It just ends up being 1. We can do dz or d theta, dz, it doesn't matter. So let's do d theta dz. Whoops, that was supposed to be a z. And recall our limits for theta were from 0 to 2 pi. Our limits for z were from 1 to 4 or 3? 1 to 4. Yeah. So then integral, this is really easy. So integral of 1 with respect to theta is theta from 2 pi to 0. That's just going to give me 2 pi. So then I integrate 2 pi with respect to z. I get 2 pi z from 1 to 4. That's going to give me 8 pi minus 2 pi. I get an answer of 6 pi for my surface area. Let's do a few more examples. So on this one, we're going to find the surface area of a cone. The cone equation is z equals the square root of x squared plus y squared. And we're going to find the area, the lateral surface area, so not the top, just the area around this thing, right, on the outside of this, from 0 to 4. Using the same idea. So, all right, we need to come up with a parameterization here. And this time now, the cylinder, the radius was always the same. It was always 1 unit away. But, any point on this surface here is a certain radius. And so recall in polar coordinates, x is always r cosine theta, so r is not constant. Y is r sine theta. And what about for z? Well, you can plug both of these in for x squared plus y squared, and hopefully you can see you're going to get a r squared cosine squared, r squared sine squared. You can factor out the r squared, and you're going to get cosine squared plus sine squared, which is 1. And the square root of r squared will just be r. And you may also recall from cylindrical coordinates, that is just r by definition. X squared plus y squared equals r squared, so this is just c equals r. As long as I can parameterize all 3 of my coordinates in terms of 2 variables, that's a valid parameterization. Of course, theta is going to go from 0 to 2 pi. And if z is really r, then I'm going to have my r value go from 0 to 4. So then next step, I got to write this vector function. So my vector valued function is going to be r cosine theta for x, r sine theta, and then just r for z. Then I want to get my partial derivatives. So I want to find r sub theta, treating r as a constant. This is going to be r times negative sine theta. So negative r sine theta. This one with respect to theta, r cosine theta. With respect to theta, that's going to be 0. Partial derivative with respect to r is just going to be cosine theta, sine theta, and 1. So then I'll do my cross product. R sub theta crossed with r sub r. And I'm going to get r cosine theta minus 0. So that's r cosine theta. For the middle one, which I have to add my negative, it's going to be the negative of negative r cosine theta times 1 minus 0. So the 2 negatives will cancel. I'll end up with r sine theta. And then r sine squared theta, negative r sine squared theta, sorry, minus r cosine theta. So squared theta. So that's going to be minus r sine squared theta minus r cosine squared theta, which can be simplified, right? If I take out a negative r, I'm going to be left with sine squared theta plus cosine squared theta, which is just 1. So this whole thing just simplifies to 1. So then I want the magnitude. Which is the square root of r cosine theta squared plus r sine theta squared plus 1 squared, I guess. This is going to be r squared cosine squared plus r squared sine squared. So you can take out an r squared, and I'm going to end up with just r squared, right? I feel like something's not right here. Oh, this is not just 1. This is 1 times negative r. My bad. That's what was wrong. Negative r times 1 is this is negative r. So this should have been negative r quantity squared. So that's going to be r squared. So then we're going to get, if you factor out the r squared here, you're going to end up with cosine squared theta plus sine squared theta, which is 1, plus another r squared. So we get the square root of 2r squared, which is root 2. And because r is always going to be positive here, that's just root 2r. So then to finish this off, I would do the double integral of root 2r. I can do it as d theta dr or dr d theta. Doesn't really matter. I'll do dr d theta this time. Keep in mind that's not polar. I'm not doing r dr d theta. That root 2r was the value of my cross product, right? So it's not like that's my polar. This is just by itself here. R goes from 0 to 4, and theta goes from 0 to 2 pi. Try this on your own, and you should get the answer of 16 pi root 2. And let's do another one. Got two more for you here. Trying to give a different variety. So here we're going to find the surface area of the plane cut by the cylinder. X squared plus y squared equals 1. So to get a picture of what that looks like, I know sometimes the challenge is visualizing what this is. Recall the cylinder x squared plus y squared equals 1. That would be like a circle of radius 1 on the xy plane, and you're just going to extend it upwards and downwards. You extend it in all directions, right? So this thing goes up forever. Now the plane y plus 2z equals 2, that's a plane that has a y-intercept of 2, so maybe over here somewhere, and a z-intercept if y is 0 of 1. So it's going to cross the z-axis here. So you can kind of picture a plane that's going down, cutting through this cylinder. And if it cuts through this cylinder, the intersection will look like an ellipse. It might look something like this. So this is what we want to find the surface area of. It's the plane, part of the plane, this plane right here that was cut by this cylinder. We want to find the surface area of that. Okay. So we need a parameterization. Let's switch to purple. So for x, it's going to be a circle. Every point on this circle, the r is going to the radius of the circle is of course 1, but we want every single radius from 0 to 1. So we're going to have, once again, x be r cosine theta, y be r sine theta. Now what about for z? The z coordinate of any point here has to satisfy the equation of the plane. So if I solve this plane for z, I'm going to get 2 minus y divided by 2. Z is equal to 2 minus y over 2. And if I split that up, that's 1 minus 1/2 y. But if y is r sine theta, then z is going to be 1 minus 1/2 r sine theta. And I've got it parameterized in terms of r and theta again. So my vector function will go r and theta is r cosine theta, r sine theta, 1 minus 1/2 r sine of theta. Okay, this might be a good opportunity to pause the video, take your two partial derivatives, r sub r and r sub theta, and then do the cross product and try to find the magnitude of that. In other words, see if you can finish the problem. Okay, so r sub r is cosine theta, sine theta, minus 1/2 sine theta. R sub theta is going to be negative r sine theta, r cosine theta, and negative 1/2 r cosine theta. Okay, if you do, so I'm going to trust, if you have trouble, you can ask me. But to save a little time, if you do that cross product of this, you should end up with the vector 0, 1/2 r, and r. So make sure you can get those values. You're probably going to need some trig identities. So then what you would end up integrating, my surface area is going to be the integral of, I have to find the magnitude of this. Whoops. The magnitude of 0, 1/2 r, r. And then it's going to be dr d theta. So what is the magnitude of this? It's the square root of this squared plus this squared plus this squared. Zero squared plus, if I square that, that's going to be 1/4 r squared plus r squared. So it looks like that's going to be 5/4 r squared. Similar to the last problem, we can break that up as 5/4. This is 5/4. So that would be the same as √5/2, right? Because that's a perfect square, r. And why don't I just pull the √5/2 out? But we're still going to have r, because the square root of r squared is r, dr d theta. R varies, remember, it was stuck inside the cylinder, x squared plus y squared equals 1. So r is going to go from 0 to 1. Theta is going to go from 0 to 2 pi. And if you finish off this integral, you should end up with √5/2 pi. Okay, one more. Save the best for last here. Best meaning probably the most difficult here. As you've seen, a lot of the parameterizations we've been using r and theta, right? I guess the first one we did z and theta. But if I want to parameterize something that involves a sphere, I'm probably going to need to use spherical coordinates for my parameterization. So here we're going to try to find the area of the surface of the, if I take the top half of the sphere, not the top half, if I cut x squared plus z squared equals 4, which is a sphere of radius 2, by the plane z equals √3, which is slightly less than 2. So that plane is going to cut right through the top part of that sphere, and you're going to be left with a little dome-shaped piece. That's what we want to find the surface area for. So what we have to remember for our parameterization is we got to go back to spherical. Remember, in spherical, x is always rho sine phi cosine theta. You should, if you're having trouble remembering these, go back and look in that section. Y is rho sine phi sine theta, and z is rho cosine phi. Now, notice every point actually on the surface, what is rho? It's the radius of the sphere, and the radius of the sphere would be 2, right? That's the radius squared. So my parameterization, if I put 2 in for all of those rows, I'm left now with x, y, and z defined with just 2 variables here. So I'll put on the surface of the sphere, rho is equal to 2. So my vector valued function, my parameterization my 2 variables are going to be phi and theta. X is 2 sine phi cosine theta. Y is 2 sine phi sine theta. And z is 2 cosine phi. So here's an example with two different variables that we haven't seen before in a parameterization, but the idea is the same. If I do my 2 partial derivatives, so I need r sub phi and r sub theta. Again, maybe a good time to pause the video and work out those partial derivatives. So with respect to phi, this is going to be 2 cosine phi cosine theta, 2 cosine phi sine theta. and -2 sine phi. With respect to theta, and that's going to be negative sine theta. So it'll be -2 sine phi sine theta. This will be cosine theta. So 2 sine phi cosine theta. And since this is just a function of phi, that's going to be 0. Okay, now the fun part. We have to do now the cross product of r sub theta. No, well, let's do phi since we did that first. Crossed with r sub theta. I, j, k. 2 cosine phi cosine theta. 2 cosine phi sine theta. -2 sine phi. Two sine phi cosine theta. Unfortunately, that one's 0. Okay, you can see there's going to be a lot of multiplication and hopefully some trig identities that are going to help us out. So doing the first cross product here, I'm going to have this times 0, which is nice, minus -2 sine phi times +2 sine phi cosine theta. So that's going to come out to be, remember it was 0 minus -2. So that'll be 4 sine squared phi cosine theta. That one wasn't too bad. Middle. This times 0. And then minus this times this. Oh, remember there's also going to be automatically a minus. So we're going to have this -0 minus, this is going to be a positive. So minus 4 sine squared phi sine theta. So when all is said and done, this is going to end up being positive. And then for my k component, this times this minus this times this, because this is negative, it's going to be a plus. So I'm going to end up with, let's see, we're going to have, if I do this times this, I'm going to have 4 cosine phi sine phi. But I am going to get cosine times cosine, so that's cosine squared theta. Minus negative, so that's going to be plus, let's put this right here, plus 4 cosine phi sine phi sine squared theta. That was a continuation. So that looks like a mess. And we have to find the magnitude of this vector. So maybe what we should do first is see if we can simplify. I don't see any simplification here, but here I certainly do. For the k component, what can we factor out? So we have the same terms here. We have 4 sine squared phi cosine theta, 4 sine squared phi sine theta. If I factor out a 4 cosine phi sine phi from this term and this term, that's going to leave me with cosine squared theta plus sine squared theta. How nice. Because that's just 1. And that's about all we can do. So now let's find the magnitude of our vector. So we have the square root. If I square this, I'm going to get 16 sine to the 4th phi cosine squared theta plus this squared, 16 sine to the 4th phi sine squared theta. And this squared is just going to be 16 cosine squared phi sine squared phi. Once again, that would be nice if we could simplify that. So you maybe take a minute and see what you can do and clean that up a little bit. For these two terms, what I'm seeing is if I factor out the 16 sine to the fourth, I get another Pythagorean identity. That's equal to 1. And 16 cosine squared phi sine squared phi. Now, is there anything we can simplify between this term and this term? It's like I can take out a 16 and a sine squared phi at least, which will leave me with sine squared phi here plus cosine squared phi. Isn't this really cool? All these nice simplifications keep happening. So that goes away. That's just 1. And then we're just left with this term, and the square root of 16 sine squared phi is just 4 sine phi. Whew. Now we're ready to set up our double integral, but what we have to do, I forgot to do this earlier, is we've got to find our bounds for phi and for theta. If you want to get every point on the top of this dome, obviously you're going to have theta go all the way around the circle. But if you recall what phi is the angle you make with the positive z-axis. I'm going to, obviously 0 I would start, but as I start to rotate this way, my limiting bound for phi is when I get to this angle right here. Let's draw that separately. So here's the z-axis. And this angle, I couldn't even draw like in the circle right here. There's the top of the sphere, right? And this is the angle I want. That's the angle that's my upper bound for phi. Well, what do we know about this? If I make a triangle out of this, remember that the equation of this plane was z equals √3. So that means this distance right here is √3. This is the radius of the sphere, which we know is 2. And if you recognize this, this is a special triangle. This side's going to be 1. And you can do a trig function to find out what phi is. If, for example, you could say the sine of phi is opposite over hypotenuse, 1/2. Or if you just recognize that, that is pi over 6. That is pi over 6. So for my parameterization here, I forgot to write it here. We're going to have theta go from 0 to 2 pi. But for phi, we're going to have that go from 0 to pi over 6. That part's a little bit tricky. So our surface area is going to be the double integral of the magnitude of r sub phi crossed r sub theta, which we got to be 4 sine phi. We can do it either way. I guess I'll do d phi d theta. So that's going to go from 0 to pi over 6. This is going to go from 0 to 2 pi. And this is a very doable integral. Antiderivative is going to be negative sine, so we'll have -4 sine, negative cosine, I'm sorry, from pi over 6 to 0. Cosine of pi over 6 is √3 over 2, so we're going to get -4. Might as well pull that out, and I'll get √3 over 2 minus the cosine of 0 is 1. Let's distribute it and let's write it the other way. -4 times -1 is 4, and then this will be minus, cancel that, 2 √3. So integrating, that's just a constant with respect to theta. 4 minus 2 √3 theta from 2 pi to 0. That's going to be 2 pi minus 0. So it'll just be this times 2 pi. That's the surface area. Whew. All right. Well, hopefully this is helpful. On the next video, we're going to talk about at least one other technique for finding the area of a surface that looks completely different. This is just one of a couple of big methods in this section of the book to help you find the area of a surface. Thanks for watching.